Welcome. So we're on chapter 6, learning objective 2, and we're going to finally start talking about this normal distribution. So most of us are at least familiar with the normal distribution, at least in passing. It's that bell curve that we hear talked about. Most data, or I don't want necessarily most, but a lot of data follows this bell curve, at least at the population and large sample size level. Now, I mean, small sample sizes may not necessarily follow that, but we'll talk more about sample sizing and sampling and all of that in a later chapter. But again, most of our larger data sources do follow this sort of normal distribution, what we call normal distribution, this bell curve. And so a lot of our statistical analysis involves using the bell curve and methods of analyzing the bell curve, but because we can apply these to so many data sources. So the characteristics of a normal distribution, here you can see a bell curve over here on the side. Now how steep or how flat the bell curve is, that varies, but the idea of a bell curve is that number one, it is symmetric. So essentially you could fold it in half. You could fold it in half on this line here down the middle, if you can see where my cursor is, this line down the middle, and it would be identical on both sides. So it's symmetric. And it's symmetric around the mean. So for a normal distribution, what we say the mean is 0. Now, I'll explain that a little bit more in a minute because you're thinking, well, the mean is not always 0. Like that doesn't make sense. But I'll explain that. For a normal distribution, the mean is 0. Also, the mean, the median, and the mode are all equal. So again, we can see here, it's in this case, it's always going to be 0. So there is a 50% probability that an observation is above the mean, above 0, and a 50% probability that the mean is, or excuse me, that an observation is below the mean in kind of that green area. So if you think of it, the green area would be the negative side, the below the mean. The kind of yellow beigeish area over here is the 50% above the mean. Now, this is also asymptotic. So what that means, or I can't really pronounce that word very well, but when you took algebra and calculus and geometry, you talk about asymptotes. Asymptotes are those lines that get really, really, really close to 0, but actually never touch 0. And this is true of a bell-shaped curve also. The tails, and what we call the tails are these areas over here to the left and the right where those two arrows are pointing, the two blue arrows are pointing. Here we go, I'm finally getting my cursor back. So here and over here, those get really close to 0, but they never actually touch 0. They never actually really touch 0, but they do get very, very, very close. So a normal distribution is described by two parameters, again, the mean and then the population variance. And remember, then the standard deviation is just the square root of the variance. So we can completely describe it by looking at the mean and the population variance. The population variance, or the standard deviation, if you take the square root, is going to tell us how steep or how flat the bell curve is. So a more varied bell curve will have a sort of a flatter distribution. A less varied bell curve will have a steeper distribution. So this is a really ugly formula here, but we're just going to talk through it. And then, of course, as we've been doing, we're going to do the actual calculations in Excel. So here we have this probability density function of a normal distribution. So this is a cumulative density function. We can calculate the area under the bell curve up to a certain point. And so if we know a random variable x and we know the mean and we know the variance, then we can calculate what is the probability that the area under the curve is a certain amount. And we'll look at some examples of that here in just a moment. Now, when we talked about a z-score back in chapter 3, I believe, this was really a prelude to what we're doing now. So the z-score is the value that any standard normal variable may assume. So when we talk about the standard normal distribution, this is that normal distribution with a mean of 0, mean, median, and mode of 0, and the standard deviation is 1. So if you have a standard normal distribution, then you have a mean of 0, a standard deviation of 1. This is a special case. And then we can use a z-score to calculate the probability that a particular variable or observation lies in a certain portion of the bell curve. Oh, let me go back. Went too far. Now, there's two ways that we're going to do this. There's a table method. There's certainly the formula method that we just looked at. We're not really going to use the formula method in this class. So we are going to look at the tables very briefly. We are going to move on and do this in Excel, but I do want you to at least be familiar with the tables, because this is something that you may be required to know or ask about. So I do want you to be familiar with the tables. So the tables are actually in your textbook. Even if you have the e-textbook, they're in your e-textbook. If you have the physical, the printed textbook, they're on page 510 and 511. So on page 510, this is the negative side. This is looking at what's to the left of the mean. And then the right side is the positive side. It's looking at what's to the right of the mean. So when we are trying to calculate the probability of a particular z-score, then we can just look, is it to the left of the mean? We'll use the table on the left. Is it to the right of the mean? We'll look at the table on the right. Then we'll look down the left column and across the top, and we'll find that table value, and that table value is our actual probability. So we're going to look at an example here on the next slide. So here we've got, this is just a short snippet of the negative z values and the positive z values on the table. So for example, if we were looking at negative 3.6, we would come over here to this negative table. We would go down the left side to 3.6 and then across, or 3.62. Then we would go across to where we have 0.02 at the top, and that would give us, for example, our probability. So we go to the 10th place on the column, and then you go take it to the 100th place by looking across the top. So again, we can find the probability that any given z value by looking at the table. So here we're told, what is the probability that the z value is 1.52? So we can go to our table. We're looking on the right side. Notice that 1.52 is to the right of the mean, so we're looking at the positive side. So we can go over here to our table, 1.5, and then 0.02 across the top, and we get 93.57%. So using this data, we could say there's a 93.57% probability that a particular observation is greater than 1.52. Excuse me, is less than 1.52. I said that backwards, forgive me. We can look at, it's the probability that is less than 1.52. So here's the way the probabilities work. They always work from left to right. You're always reading it from left to right. So if you're looking at the probability that is less than, so that means the green area in this graph here, then you're looking at the table value. If you want the probability that it is greater than, meaning you're wanting to measure what's in the right side, what's in the tail, then you have to do that 1 minus, right? And we've talked about that before, and we've done that before in previous chapters, and we're going to do it again. So if I'm wanting the greater than, I'm going to do 1 minus the table value, because then greater than is looking at this yellow portion here in the chart, whereas the less than is looking at the green portion here in the chart. So you're always reading from left to right on your graph. And so thinking about it that way, the less than is measuring from here to the left, whereas the greater than is reading from here to the right. And that would be 1 minus what's on the left. So again, if we're wanting to look at the less than sign, so here we're told what's the probability that a particular observation or value is less than a negative 1.96 or less than or equal to a 1.96. We're going to look in the left-hand table. We're going to look 1.9 down the left side and 0.06 across the right. And so we get 0.0250 or 2.5%. So there's a 2.5% probability that a value is less than or equal to negative 1.96. So then if we wanted to calculate, well, what's the probability that it's greater than negative 1.96, we would say 1 minus 2.5%, which would give me 97.5%. Now, most data, while we said most data follows a normal distribution, most data is not a standard normal distribution, okay? So any normal distribution, any normally distributed variable with a mean of mu and a standard deviation of sigma, we can transform into a standard normal distribution by calculating the z-score. So again, even if your data doesn't have a mean of 0 and doesn't have a standard deviation of 1, we're going to standardize the data, and that's the verb we use, by calculating its z-score. And so essentially we're converting it into a standard normal so that we can apply all of these statistical principles that we can use with a standard normal distribution. So by standardizing it, and that's the verb that we use, you're going to calculate the z-score and essentially convert it to a standard normal distribution. So the z-score is really easy to calculate. It's just your random variable x minus the mean divided by the standard deviation. And then by doing that, you're essentially making the expected value of z, which remember the expected value is the mean, be 0, and you're making the standard deviation be 1, so that, again, you can apply all these standard normal distribution principles. So for any value of z, if z is greater than 0, then we know it's above the mean, it's on the right-hand side. And if it's less than 0, we know it's below the mean, it's on the left-hand side. So again, a positive z-score tells us how many standard deviations the observation lies above the mean. And then a z-score is 0 is exactly equal to the mean. And then a negative z-score tells us how many standard deviations it's below the mean. The observation or the random variable is below the mean. Now, if we know the z-score, for example, or we want to know the z-score, we can calculate then what is the random variable that would give us that z-score. So we just rearrange that formula that we looked at by saying mu plus the z-score times the standard deviation. So for example, if I wanted to know, and we'll look at an example of this, if I wanted to know what is the test value that would put me in the top 10%, then I could calculate the x value that way. If I want to know what's the value that is in the top 10%, that's the z-score. If I want to know what's the variable, then I calculate the x, but I have to know the z-score. So we're going to jump over here to Excel in just a moment. So this is just the formulas that we're going to use. So if we have a standard normal distribution, which means the mean is already 0 and the standard deviation is 1, then we'll use these top two formulas right here. And notice it's norm.s and then distribution or inverse, and we'll talk about what that means in a minute. But most of the time, we're not going to have the standard normal. So most of the time, we're going to use these bottom two formulas, which are just norm dot whatever, and that's calculating, standardizing it. So we're calculating the z-score, for example, or calculating the x value given the z-score. So let's look at a couple of examples. So here we're told we have scores on a management aptitude test. They are normally distributed. They have a mean of 72 and a standard deviation of 8. Now, since the mean is not 0 and the standard deviation is not 1, this is not a standard normal distribution. However, again, by standardizing this, by calculating the z-scores, we can still apply these same statistical principles. So the first question we're asked is, what is the probability that a randomly selected manager will score above 60? Okay, will score above 60. So this is asking, what is the probability that X is greater than 60? So notice we're looking at what is the probability that the green area in our graph here will be above 60. Now remember, our mean was 72, so 60 is below the mean. That's why it's on the left side. But I'm wanting to calculate what is the probability that it's above this, that it's greater than. So this is my clue then that I'm going to have to do that 1 minus business, because remember, we automatically were calculating from left to right, and I'm wanting to calculate from right to left, so to speak. Maybe that makes sense, maybe that doesn't. So first I need to transform my x variable to z, and so I'm going to use that formula. I'm going to say the variable of x minus the mean of 72 divided by 8, and I get negative 1.5. Now we know that it's a negative. We're expecting it to be a negative because 60 is below the mean of 72. So we know that it falls on the left-hand side of the bell curve. So now I could pull out my handy dandy tables. I can go to the left table because it's a negative. I can look up 1.5. And if I do that, I find that 1.5 is 0.0668. Now that means there's a 6.68% probability that someone will score less than 60. But I want to know what's the probability they're going to score greater than 60. So I'm going to say 1 minus that. And that gives me 93.32%. So again, the 0.668 or the 0.0668 is this yellow area that was calculated here. And since I want to know the green area in this case, I'll say 1 minus that value, and that gives me 93.32%. Now we're going to jump over to Excel and do the same thing in Excel. So I want you to be familiar with the tables, but I also want you to know how to do this in Excel. So here we are in Excel. We don't have a Chapter 6 worksheet. I just pulled up a blank worksheet. I went ahead and entered at the top. You'll notice I entered the mean of 72 and the standard deviation of 8. I just wanted to have that there so I can refer back to it easily. So I want to know, what is the probability that the score on this test is greater than 60? So first of all, here I'm going to start my formula. Equals 1 minus, because it's a greater than, I have to do 1 minus. And now I want to enter a formula. I want to enter a formula for the normal distribution. So I'm going to click on More Functions. I'm going to go to Statistical, and I'm going to scroll down here to the ends. Here we go. Now, I don't want to choose the normal.s because this isn't a standard normal distribution. Remember, I'm converting it to a normal distribution. So I'm going to choose just the norm.dist. So when I open up this, it tells me x, first of all, is what is my observation, what's my variable that I'm looking for. In this case, that was 60. I want to know what test scores would be great, the probability the score would be greater than or equal to 60. My mean, I can type in 72 here. I could also put in a cell reference to reference cell B1. My standard deviation is 8. And then here under cumulative, we want to put a 1 because we're calculating that area under the curve. And so that is the accumulation of the area under the curve. So I definitely want to put a 0. If you put, excuse me, put a 1, I said that backwards. If you were to put a 0, it would calculate the height of the curve. Now that may be useful if you're trying to graph it, but for what we're doing, we want to know the area under the curve so we can calculate that probability. So we want to make sure we put a 1 in there. So now I'm going to say okay. Now notice my formula up here is 1 minus the normal distribution, and it gives me again 93.32%, which was approximately 93.3193%, which is very, very close to what we got using the table. It's slightly off to a little bit of rounding, but not much. All right, so let's jump back to our PowerPoints now. All right, so we looked at what we're going to enter in Excel. Your formula in Excel for the normal distribution is X, your observation or your variable, mu, your mean, sigma, your standard deviation, and then again putting a 1. So we entered our formula as 1 minus, and that calculated for us again that probability. And we got 93.32% approximately. All right, so let's look at a different question now. Using the same data, what is the probability that a randomly selected manager will score between 68 and 84%? Okay, so now we're wanting to calculate, we actually need to calculate two different probabilities. We need to calculate the probability that is less than 84, and then subtract from that the probability that is less than 68 so that we can kind of get that middle value. So here we're calculating again the middle value, the value between 84 and 68. Okay, so in order to calculate the value that X falls in the middle, we have to calculate two probabilities. Again, the probability of the area from 84 below, and then the probability of 64 below, and then we subtract those, and that will give us our middle value there. PowerPoint, there we go. So we're going to enter our formula into Excel in just a minute. So first of all, we have the probability of 84 and below, and then we subtract that, the probability from 68 and below, and that's going to give us that middle value there where we can determine what's the probability that they score between 68 and 84. So let's jump over to Excel and try this now. So here I am back in my same Excel spreadsheet. So again, I can go up and enter the formula just like I did before, or I can just type it in. I'm just going to type it in this time. So I want to do the 84 first and then subtract from that the 68. So equal norm dot distribution. And notice how it gives me a clue here. I want to calculate the value of 84 to the left, where my mean is 72. I'm going to go ahead and use my cell reference there. My standard deviation is 8, and then I definitely want it cumulative, so I'm going to put a 1. Close my parentheses. Now I'm going to subtract norm.dist. Now I want to subtract the area that is 68 and below, so 68. Again, my mean is 72, my standard deviation is 8, and I definitely want it cumulative, and so now I get 62.4655%. So about 62.5% of managers will score between 68 and 84. So just a little bit below the mean of 72, and then a little bit above the mean of 72, about 1.5 deviations above. So let's jump back now to our PowerPoints and look at our next question. So this question is asking us, what is the lowest score that will place a manager in the top 10%? Okay, so if we're looking at, really wanting to look at what's that top 10%, that's the far right tail of our distribution. So really we're wanting to know what's the lowest score that would or what's the top score of the 90th percentile, right? What's the top score of the 90th percentile is another way that we could ask the same question. Come on, why is my PowerPoint not responding here? So the top 10% is the 90th percentile. So we can say what's the lowest score in the 10% is also the same as saying what's the top score in the 90th percent. So what is the probability that X is less than 0.9? Now, we are wanting to calculate not the z-score here, we're wanting to calculate the variable, right? We're looking for X. So this is where we're calculating the inverse. It's called the inverse because you're not looking for the z-score, you're looking for X. So I want to know what is the variable here that would put me at the top of the 90th percentile, in the top of the 90%. So the formula that I'm going to use then is that norm.inverse formula, where the first term is the cumulative probability. In this case, that would be 0.9 for 90%. Then the mu, the mean, and the standard deviation. So let's jump over to Excel and try this one now. All right, so here I'm going to go back into my formulas. You can do this, of course, any way you want to, but I want to go back into my statistical formulas. Scroll down here to my normal distribution. So, oh, I clicked the wrong one. Pardon me. Jump over here. I want to scroll down to my normal distribution, but I want to make sure I'm calculating the inverse. So again, the probability is, remember we're going from left to right, so 0.9. My mean was 72. My standard deviation is 8. And so I plug this in and I get 82.25. So the lowest a manager could score and still be in the top 10% is 82.25. Or you could say a score of 82.25 is in the 90th percentile for test scores. So now we're asked, what is the highest score that will place a manager in the bottom 25%? So, in other words, what's the lowest? Oh, forgive me there for a moment. Oh, so we are calculating what is the probability that X is less than 0.25. What's the probability that you're going to score in the bottom 25%? So again, we're going to use that inverse formula because we're looking for the X value. And so we're going to use the same formula, except our cumulative probability now is going to be 0.25. Our mean is 72 and our standard deviation is 8. So let's jump back over to Excel. So here I'm going to type in my formula this time. So remember, it's norm.inverse. And so my cumulative probability in this case is 0.25. My mean is 72. Again, I'm going to use my cell reference just because I want to. And my standard deviation is 8. And so a score of 66.6 is the bottom 25%. Okay, so if you score 66 on this aptitude test, that's in the 25th percentile. All right, so this is the end of video 6.2. We've got one more video here in this chapter where we talk about exponential distributions, and then make sure that you go in and do your practice in Excel, do your homework, and your SmartBook assignments.